Hello, everyone. This is Spencer Snowling from Hatch, and I have my colleague Jacob Barkley with me here today. And welcome to the first webinar for 2022, where we're going to be talking today about how to connect GPSX to Python and be able to exchange data back and forth and to be able to control the simulations and do some interesting custom advanced simulation analysis. So as always, we are going to allow you to ask questions while we're going through the webinar today. So if you go to your GoToWebinar dashboard, you'll see the usual questions panel. So if you pop that out, you can type your questions in there. We'll let those kind of accumulate up as we're going through the webinar today. And then we'll stick around at the end to answer as many of those as we can. So our plan for today is that we are going to talk a little bit about why we added this connection to Python into GPSX in the last version that came out, version 8. We're going to talk about how to take advantage of that connection, to look at the tools that are available. And we will also be doing a number of desktop demonstrations. So this is a very practical tool. So we're going to be having, I think, even more than usual actual live desktop things running. And you'll be able to see how we took advantage of the features that we have added to software. So we're going to run some dynamic simulations where the Python code that we will have will interact with the simulation while it's running. We're going to do a sensitivity analysis across multiple variables at the same time and produce some very nice output as well. And then we're going to use it to connect to another piece of software called PHREEQC that does equilibrium calculations, and you can see how we can take advantage of the PHREEQC API to be able to pass information back and forth while GPSX is running. So there's a number of other advanced use cases that we'll also discuss very briefly about other things that you could potentially do with your Python connection. And then, as always, we'll answer as many questions as we can when we get to the end of the webinar. Okay, now I just want to make one thing here, mention this up front. We're going to assume and speak as though those attending the webinar today are somewhat familiar with Python. So we're going to be referring to the structures of the different parts of the Python programming language, and we're going to put some Python code up on the screen and discuss the various libraries that are available. So really, we're not going to be teaching Python. We're really just going to be focusing on how to use Python in its current format and connect it to GPSX. If you would like to spend some time sort of familiarizing yourself with Python and then come back and be able to take advantage of this and want to go and review all of the things we're talking about today, this webinar will, as always, be recorded and will be uploaded to the Hydromantis YouTube page that is available at youtube.com/Hydromantis. So you'll be able to pop up there. If you go to the playlists and select webinars, then you'll be able to see all the webinars that we have available there. There's a lot of Python resources available out there on the web to be able to take advantage of and learn, basically right from scratch, how to understand Python, its structures, and how to use it. Here's a number of different things that you might want to take advantage of, different websites. I personally started myself learning Python from scratch using W3 Schools, and I thought that was really fantastic, but I know many of these other ones are great as well. Okay, so now we're going to move on to the actual meat of the webinar here. We're going to talk about adding Python functionality to GPSX, and at this point I'm going to hand it over to my colleague Jacob. So Jacob, I'm passing over the presentation to you now, and you can take it away.
All right, thank you, Spencer. So the first thing that we're going to address is why did we actually add Python to GPSX in the first place? Because GPSX has been around for a very long time, but it wasn't until recently, in the most recent major release of GPSX version 8, that we actually added Python. So, well, GPSX, it has a lot of applications and a lot of variables and a lot of visualization options to it as is. But at the end of the day, this may not always be generalized enough to do exactly what you want to do with it, which is something that you can do with Python. Additionally, Python is a very easy to learn and pick up programming language that's very well documented. A lot of the applications we're going to go through today were already available in some way in GPSX using things like Axle code, but that required an understanding of both Axle code and GPSX workings, whereas Python makes that a bit easier to handle. Additionally, Python has a bunch of open source development options available to it, where people are constantly making free libraries for a wide range of tasks that can make your life a lot easier and just make other tasks possible that weren't before. Additionally, Python's a great tool for actually automating repetitive tasks that you may be doing in your simulations. So with that out of the way, let's look at how we actually go about using Python in GPSX. So the very first thing to note is that Python is included as a part of the GPSX Pro Plus license. So you're going to need that license to be able to use Python in GPSX. If you aren't sure what license you have, or you'd like to look into actually upgrading to the Pro Plus license, please feel free to reach out to us at info@hydromantis.com, and we can answer any questions about that and help you go through that process. Additionally, it's worth noting that Python is going to be run internally in GPSX, but you can feel free to use any code editor or text editor that you're comfortable with. For example, I tend to use the PyCharm IDE, but you can use whatever you want. And then for this particular webinar, we're going to be using Notepad++ just because it's a very user-friendly and easy to read interface that won't add any more complication to these examples. So with that, how do you actually get to Python? Now, we made a handy tool called the Python Script Manager that handles all of Python's functionality when you're in GPSX. And to get to the Python Script Manager, you need to be inside of simulation mode in GPSX. It's not available when you're in modeling mode, only simulation mode. And then when you're in simulation mode, you can access it by going to Tools on the main toolbar and then selecting that Python Script Manager option. And when you do it, it's going to take you to our Python Script Manager, which looks like this. And there's a couple of important features in the Python Script Manager. The first thing is the file list. So the list of all the files and Python files that you're currently including in your GPSX simulation. So for example, in this case, I have 3 files in the Python Script Manager that are located on my desktop. And right now the calibration.py file is selected from that list as indicated by the blue highlight on it. Next on the right, there's 4 buttons for actually doing file management, where the first button is the New button, which allows you to create new GPSX template files for Python that immediately get added to the Python Script Manager. The Add button, which allows you to add Python scripts to GPSX that you may already have made on your machine somewhere else that you want to now use in this simulation. Remove, which allows you to remove the currently selected script from the file list. And then Edit, which will allow you to open up the selected script in a file editor. And you can, by default, it will open it in Notepad. But as I mentioned, we're going to be using Notepad++ in this example, or these demonstrations. And you can specify a custom editor that it will open in. Next is our simulation controls, where you have 2 buttons available to you. You have a button to actually run the script, and then the currently grayed out X button allows you to abort a running script if you need to exit for any reason. Next, we have the preferences, which is indicated by by the gear icon, which will open up the preference menu for Python and GPSX, as well as a clear all variables button, which is indicated by the eraser. And the final important feature is just the console window. This is where any outputs of your Python script will be printed, such as print statements or any errors that may come up while you're running scripts. So next, if we were to press this preference button, it will take us to the Python preferences menu, which you can see on the screen now. And similar to the Python Script Manager, there's a couple of important features. The first feature is the distribution. So GPSX comes prepackaged with 2 distributions of Python. It comes with version 2.7 and version 3.7. We're going to be using 3.7 in this demonstration, but you also have the option to add other versions of Python if you want to by selecting the other option and then providing the version you're using and then the path to the Python executable. The next option is the editor field, which, as I mentioned, is it specifies the text editor or IDE that you want to open up scripts in when you press edit. So I just have it pointing to Notepad++ on my machine. Finally, we have the jar class path field, which allows you to add Java scripts, Java jar files to your to be accessible for use in Python scripts. So if we were to create a new file, this is the template that GPSX will create for you by default. And there's a few things here. It comes with 3 predefined function definitions and 1 function call. So let's go through them quickly. The first function definition is the start function. Now this function is going to be executed exactly once in a GPSX simulation triggered by Python, and it will be executed immediately at the start of the simulation. The next function definition is the sint function. Now this function will be executed at every communication interval. And if you're not familiar with a communication interval, it has a direct analog in GPSX where you can set the communication interval in this bottom menu here, and it allows you to specify when GPSX will essentially pause. And in that function, at every pause interval, you can then do things with Python to apply logic to your simulation at that set interval. The final function definition in the GPSX template is the EOR function. Now the EOR function will be executed exactly once at the end of the simulation, just like how the start function will be executed exactly once at the start of the simulation. The final thing in the template is the runSim function call. Now this function is what actually is responsible for executing the Python script and then executing GPSX, what causes GPSX to run. And it does that by calling the 3 function definitions in their appropriate order through the simulation. So the GPSX API, which comes for use in Python scripts to actually interact with GPSX, comes with over 30 recognized functions. And there's a detailed comprehensive list of these that you can find in the user manual's appendix, where it has the name of the function, what parameters it takes, and a detailed description of what that function actually does. But there's about 7 that I think are very important to understand, and they're going to be ones that we use throughout our desktop demonstrations a bit later. But the ones that I think are important and you'll need to know are the set tstop, set sint, runSim, GPSX set value, GPSX get value, GPSX set scenario, and GPSX reset all values. And we're going to show how they're used in our demonstrations a little bit later. So as I mentioned, a really major advantage of Python is its wealth of open source libraries that are available to it to do a wide range of applications. And just like if you're using vanilla Python, the Python in GPSX can install packages using the pip package manager. And if you ever want to install a package, usually the best place to look for instructions on how to do that is the particular library packages documentation. It usually is one of the very first things in the documentation you'll see is the actual command to install the library. We're going to be using a couple of libraries in our demonstrations, but one that I want to highlight first is just matplotlib. So now matplotlib is a plotting library. It's very detailed and allows you to have very fine control over a variety of images and plots that you may want to make. They can be static, animated, interactive, but it's just a really good plotting library. And on my screen, I'm showing the very front page of the matplotlib documentation. And one thing to point out is right at the very front, very start of the documentation is instructions on how to go about actually installing the library. So you get your pip command right there from the documentation. So if you actually want to go about installing this library in GPSX, the very first thing you need to do is open your command prompt and navigate to the GPSX folder on your machine. Where for me, that's just directly on my C drive in GPSX 8.1. So once you're in there, I'll just open up and show you. For anyone who's not familiar with what the GPSX installation folder looks like, it looks like this. There's a bunch of directories on here, but there's 2 in particular that we're interested in for Python. They're right here at the bottom, the Python and Python 3.7 folders. Now, each of these folders corresponds to one of the default distributions of Python that's included in GPSX. Where Python, just the Python folder is for Python version 2.7, and then the Python 3.7 folder is for Python version 3.7. And as I mentioned, our examples are going to be using Python version 3.7, so we're going to navigate into that folder. So once I am in that folder, then I can use the pip command that I got from the matplotlib documentation to actually install it. So all you have to do is copy and paste it into the command prompt. But you need to make sure that you preface that function or that command with the Python-M flag. Now this is important because the Python in the GPSX installation isn't usually the default Python installation that you may have on your machine. And this command just tells Windows to make sure that it uses the GPSX executable in the folder you're currently in to install the library, and it makes it accessible in GPSX. If this command isn't included, it will likely be installed in a directory that GPSX can't access. So after you run that, you'll just get an output that will show that we collected the matplotlib library, and as well as any dependencies that need it, downloaded them and installed them, and then just a message at the bottom to tell you that the installation of the library was successful. So with all of that, how do these things actually come together to interact with each other? And one easy way and a good way to think about it is that GPSX is essentially an object inside of Python when you're using a Python script to execute GPSX simulations. And this allows you to control inputs and output operation directly in GPSX. So this image here, it has a Python script on the left and a GPSX interface on the right. So when you execute the Python script, the first thing that happens is you can feed in information to set your inputs in your simulation to get the simulation definition that you want. Then, as it continues, information is fed back and forth between Python and GPSX, allowing you to apply complex logic or whatever you may want to do in your GPSX simulation through Python. And then at the end, you can take any information that you want from GPSX and then bring it directly out into Python, allowing you to do any more complex analysis that you may want to do. So with all of that out of the way, let's now actually look at a demonstration how you can use Python to drive a dynamic GPSX simulation. So this first demonstration, the main things that we want as takeaways from this is first, how you can manipulate external data using Python automation. Now, GPSX has the ability to read in files currently, but by using Python in addition to GPSX defaults, you can add in things like data cleaning and just general formatting that you can do with Python rather than having to do it manually. Additionally, we're going to touch on some more custom and complex control systems that you could implement with Python that go beyond the default built-in objects in GPSX. And for this particular example, we're going to be using two libraries that aren't included in vanilla Python that's included in the GPSX installation. We're going to use Pandas version 0.25 and NumPy version 1.17. So let's actually take a look at a GPSX layout now. So the layout that we're looking at right now is a water treatment facility that's treating river water using membrane filtration to remove the solids. The effluent from that is then fed to a neutralization tank where we have an acid and an alkali, a base dosage that allow us to actually control the pH that's leaving the neutralization tank. We then have a little bit more tertiary treatment before it is released from the plant. But we're mostly focused on what's happening in this neutralization tank and our influent. So as mentioned, to actually access Python in GPSX, you need to make sure that you're in simulation mode, which we are, and then you can navigate to Tools, Python Script Manager, and this will open up the Python Script Manager interface. For this demo, I've included two scripts that we're going to be using for the demonstration. So the first one we're going to look at is this run simulation.py file. So make sure that it's selected just by clicking on it so it has that blue background. And then you can press edit where it will open it up for you in your default text editor. As I mentioned, we're going to be using Notepad++ for this example. So the very first thing to notice in this script is we're not using any external functions beyond the default ones that are included in the GPSX Python file template. So let's step through what we're actually doing. The very first thing in our start function is we're using the GPSX set value command to set a value in our GPSX simulation, where this cryptic tag corresponds to the influent flow that's coming in the plant. So we're assigning it a value of 2,000 meters cubed per day. Next, we use the GPSX set t-stop function, which is another unique recognized GPSX function, and it sets the length of our simulation. By using a value of 5, we're saying that we want our simulation to run for 5 days. The next function that we have from our template is the sint function. Now, this is just applying a little bit of logic to actually set a value in our communication interval. So what this is doing is it's looking at the t value, which is the time elapsed in our simulation. It's retrieving that from GPSX by using the GPSX get value function, which will just give us the value that it currently corresponds to at this communication interval. And then it uses the Python modulus operator to see if a multiple of a day has been elapsed. So we only want to be applying this logic if we are on a new day, essentially. So 1, 2, 3. Then we just apply a little bit more of a control over this to make sure that we're not setting the value at b equals 0, so the very start of our simulation, because we did that in our start function. And we're also making sure that we don't apply anything when t is equal to t stop. So we don't want anything to be applied at the end just because we're not looking past our t stop. Mm-hmm. So once we have that, we just do a very simple application where we set the value of the influent again. But what we're doing is we're collecting the value of the current influent coming to the plant using our GPSX get value function again, and reducing that by 200 meters cubed per day. So every day we have 200 meters cubed flow less coming into the plant. Finally, we have our EOR function. And all this is doing is we're just pretty printing some results to show how our simulation ran. So all we're doing is at the end of our simulation, we're going to get our final influent flow, our final effluent pH, and our final effluent alkalinity. And we're just retrieving those by using our GPSX get value functions. Finally, to actually run the script and run the GPSX simulation, we start with our GPSX reset all values function, which is another unique recognized function in GPSX that makes sure all of the values in the GPSX simulation are reset back to their default values from when the simulation was built. And then finally, we call our run sim to actually execute the simulation. So let's go back to GPSX and see how that actually runs now. So I have this selected. I'm just going to press the run button. This will execute our dynamic simulation, where you can see our t-stop is set to 5 days like we want it to be. Our simulation starts with an influent flow of 2,000 meters cubed per day, and then every day it reduces it by 200 meters cubed. And then finally, in our console window, you can see that we output the results of our simulation. So our final influent flow is 12,000 meters cubed per day. Likewise, you can see our effluent pH and our effluent alkalinity at 5 days. So let's take this example a little bit further and see what else we can do with Python. So we have this control pi script. So let's open that again in Notepad++. So the very first thing you'll notice is we're importing libraries now. So we're importing pandas and we're importing NumPy. And the very first thing we do is we use pandas to read in an external Excel file. So let's take a look at what this Excel file actually looks like. So in our Excel file, we have 3 columns. We have a time column, a flow column, and a pH column, where this time column, it corresponds to the number of days that have been elapsed since our observations started being made. Our flow rate corresponds to what our influent flow rate to the plant is. And then our pH corresponds to what our influent pH is. Now, there's a couple of obvious things that I did to this, this data set. And namely, we introduced some outliers. So right here, we have our flow set to an influent flow of 0 meters cubed per day, which is very unrealistic and could lead to a lot of problems in our simulation by giving it very poor inputs, and it would give us results we wouldn't expect. Similarly, we have a pH of 1 pH unit, which we also is probably an outlier, not something we would want to include. One other key feature in this data set is there's a bunch of empty cells in our flow data column. So those are things that we also have to consider how we're going to handle. So if we go back to our Python script, let's look at how we're going about handling all of these anomalies in our data set. So the very first thing we do is we want to create just a simple report that tells us how many outliers are in our data set. And as this was a setup example, we know what our outliers, what bounds we can kind of expect them to be in. In practice, you'll need to spend a little bit more time thinking about what an outlier is and just designing your outlier detection, but for this simple example, we know what our ranges are going to be. So we're just going to take a look at what we find to be an outlier, which we'll define as any flow rate that is greater than 7,500 meters cubed per day and any flow rate that's less than 500 meters cubed per day. Similarly, for the pH, we'll say that any pH less than 4 or greater than 9 pH units is an outlier. And then we create one other report at the start of our script, which is to identify the number of empty cells. So we're just going to print out how many not a number cells are in each of these columns, just to get an idea of how many empty cells we have in our data frame. Then we go about actually doing something about our outliers. So we want to get rid of them. So we're just going to do a very simple screen where we use those same values we used for our report and say that if it is outside of our expected ranges, that it's an outlier, and we're just going to assign that value in our data frame to be a not a number field. Now that we have those empty cells, we've removed our outliers, let's actually clean the data set a bit. So for our pH, we're going to interpolate any missing points because we know that that's a complete data set. So anything missing will be attributed to an outlier. So we're just going to use built-in pandas functionality to use interpolation, just simple linear interpolation. Conversely, we saw that there was a lot of missing data in our flow. So interpolation may not be as useful because there's not as many points to interpolate from. So we're just going to use built-in GPSX functionality, where if you don't assign a value, GPSX will just continue to use that same value. So we're just going to carry forward that way using GPSX functionality. The last little bit of setup we do for our data frame is we just assign the time value to be our index, just to make it a little bit easier to access our data. Now, one thing I didn't mention, but is very important to note, is we've defined our DF, so our data frame. We're saying that that is a global variable. Now, the reason we're doing that is because the default GPSX functions in the template, they don't take arguments. So if you want to use an external variable inside of one of those functions, you need to define it as a global variable so that it's accessible and you can do things with it. So we make DF a global variable so that we can edit it in our EOR, our sint, and our start functions. Okay, with that, let's actually move on to our start function. So what are we doing here? The very first thing we're doing is we're setting a value, and this is for flow type WINF. Now, this is a variable that allows you to specify the type of flow that's entering the plant. If you look at it in GPSX, it's a drop-down menu where you have options for data, sinusoidal, and diurnal. Now, we're assigning it a value of 2, and that's because we want our influent flow to be sinusoidal. And 2 is the second entry in that drop-down menu, which corresponds to sinusoidal. And then, like before, we set our t-stop, and then we use another new GPSX function, the setSint function, which allows us to specify what our communication interval actually is. So we're going to set it to be 0.05, which means that at every 0.05 days elapsed, our GPSX essentially pauses and allows us to do logic in our sint function. The last thing we're doing in our start function is we're filtering our data frame so that we get the first row. And we know this row corresponds to t equals 0 days. So we're going to take those values in t equals 0 days, and we're going to assign the observed flow rate and the observed pH to be our initial values of flow and pH in our simulation, just so we're starting from the same point as our data set. We move on to our sint function. We're now doing logic to actually follow the data file. So the very first thing we do is we get our value of t from the GPSX simulation, so how much time has been elapsed. And then using pandas indexing, we get every index, because we made our time elapsed our index, anything that's less than our current simulation time. And then we index that to get the last value, so we get the most recent observation that's occurred prior to or at our current simulation time in GPSX. And then with those values, we just update what GPSX is using. So we get our flow value and we get our pH value. If our flow is not empty, then we update it to be our newly observed flow. Otherwise, GPSX will just keep using its same flow value. Likewise, if our pH is not empty, then we update it to be the new pH value. So the other thing that we're doing in our communication interval is we're introducing a controller. Now, what we're interested in controlling in this simulation is the pH that's leaving our neutralization tank. And if you recall from the layout, we have two ways of doing that. We can dose acid or we can dose base. So what we do is we get the pH that's leaving our neutralization tank and we say, if this pH is greater than 7.6, then our pH is too high, so we need to dose acid to reduce our pH. And we do that by getting the influent flow to the plant and multiplying that by a constant and assigning that to our acid dosage rate. And we're doing that just so we have a bit of a flow-paced dosing. Similarly, we set our base dosage to be 0. Conversely, if our pH is too low and it's less than 7, we do the same thing, but this time we set our acid to 0 and set our base dosage to a constant times the flow rate. And then if neither of those are true, meaning that we're in our desired range, we just turn off both our acid and base dosing. The last thing that we do in our communication interval is we have a running total of the total amount of acid and the total amount of base that we dose in our simulation. So what we're doing is we're getting our dosage rate, which we just set above, and then we multiply it by our communication interval to find out how much chemical in meters cubed we're dosing in that time period, and we just have a running total going. Now, similarly to before with our DF variable, these total acid and total alk variables are contained in our sint function. Now, you can't return from the sint function or the start or EOR, so we define them to be global variables so that they're accessible to do things with outside of these functions, and we can do further analysis on and after the script is run. So finally, our EOR function. In our EOR function, all we're doing is we're just printing out the total mass of acid and base we used across our simulation. Now we do that by getting our total acid and total alk variables that were global, so now they're accessible in this other function that they weren't defined in, and we multiply it by the density of that chemical by getting the value of the density from GPSX, and then just convert it to kilograms. Finally, we make sure our GPSX simulation is using the default values from when it was built and run our simulation. So once again, let's go back to GPSX and see how this is running. So if I have this selected and I press run, you'll notice that, like before, we're using a stop time of 5 days, but this time when our simulation runs, it has dynamic behavior in it. So our influent flow is changing magnitude based on the data file and exhibiting sinusoidal behavior because we defined our influent flow type to be sinusoidal. Likewise, our pH is showing dynamic behavior because it's reading in the data file and using those values to be assigned to what our influent pH is. Now, if we look at our neutralization pH leaving, this black line, you can see that our controller is working. It is keeping our pH in the range that we expect it to be. And then you can take a look at our acid and base dosing, and you'll see that our controllers are turning off these dosings on and off as needed to make sure that our neutralization tank pH that's leaving stays at an expected value. So you can see that our controllers are working and we are dosing. And then finally, if you look at our console, we can see how much acid and how much base we dosed across that simulation. Okay, let's go back to the slides for a bit now, and we'll talk about what our next simulation is what our next demonstration is going to be. So now we're interested in looking at a multivariate sensitivity analysis. So a multivariate sensitivity analysis, you have the ability to do sensitivity analysis in GPSX as is. Currently, there's the ability to do sensitivity analysis in GPSX, but you're kind of limited to just two variables. Your one manipulated variable and your one variable that you're seeing how it is impacted by the manipulated variable. Through the use of Python, we can do more complex multi-dimensional sensitivity analysis. Additionally, we can apply advanced plotting techniques such as using matplotlib to get just more control over our plots and be able to show more things than you could in a GPSX plot. Additionally, we're going to focus on how you can simulate, how you can automate simulations in GPSX with Python. And just as before, we're going to be using some external libraries. So we're going to be using NumPy version 1.17 in this demonstration and Matplotlib version 3.03. So if I bring up the GPSX layout, this time we're using a wastewater treatment plant instead of a water treatment plant, where all we're doing is just very simple COD removal and nitrification. So as before, we're going to go open our Python script manager, and we'll take a look at what this sensitivity analysis.py file is doing by opening it in Notepad++. Now, one thing to note right away is this simulation, or this script, is a little different than before. As you can see, we've defined some additional functions that we're going to be using to complement the built-in GPSX functions in the template. But we'll start at the top, and the very first thing we're doing is we're importing NumPy and Matplotlib. Now, one thing to note is when you're importing Matplotlib for use in GPSX, you need to use this matplotlib.useAGG function to assign it to the AGG backend, just so you have the ability to create the plots and access them in GPSX. So now let's go down and take a look at our main function. So in our main function, we create 3 lists, where the first list is a scenarios list, and this has the name of scenarios that are defined in our GPSX layout. Now, that layout that I showed you has 3 scenarios defined in it: a low flow, a mid flow, and a high flow, where these are the same scenarios, where the only difference is the amount of flow rate coming into the plant, where low flow has the lowest and high flow has the highest. So we have those in a list, and we then also use Python to make 2 other lists. One that's going to correspond to the volume of the aeration basin that we have, and one that corresponds to the wastage rate from our secondary clarifier tank. Say we're trying to design these and we want to look at these specific ranges as possibilities for our design. Now, the first thing we do is we feed in the volume and the wastage list, this NumPy mesh grid function, which will create coordinate matrices for us, which allows us to just have a way to look at every single possible combination of volume and wastage rate. We then create a scenario results dictionary, where we're going to store the results of our sensitivity analysis for plotting later. So this library will have an entry for each of our scenarios and will contain a solution set. We then go into this for loop, where we loop through every possible scenario, and we feed it to the this create surface function that we've defined outside of the default GPSX functions, and we give it the name of the scenario in our 2 coordinate matrices. So let's see what this function is actually doing. So if we scroll up to our create surface function, the first thing we do is we use a new GPSX recognized function, the GPSX set scenario function, where that takes the name of a scenario that you have defined in your GPSX layout and feeds it to that. And then that function tells GPSX that we want to use this scenario for the simulation that we're going to run. So we feed it the name of our scenario, so that, for example, if we have low flow first, we're going to be using the low flow scenario. We then create a results matrix just by using NumPy again, which will have the same dimensions as our coordinate matrices. Then we loop through every possible combination of wastage rate and volume. And what we want to do is we want to run a simulation where we set these values so that we have every combination in our solution matrix. So we set first the volume, and then we set the wastage rate. And we specify that we're going to be using a stop time of 0 days. So this is going to be a 0-day steady state simulation. And like always, we're going to make sure that we're using our default settings. Then we call runsim. So let's go into our GPSX function now and see what our simulation is actually doing. First, note that start and sint, those don't actually have any differences from the template. They just have a pass call, and they won't actually do anything because we're not interested in having any logic added to start or sint. But we do make a change to our EOR function. First, we define a global variable, effluent ammonia, and then at the end of the simulation, we assign the effluent ammonia global variable to have the value of the ammonia leaving our plant. So with that global variable, that we can now access that in our create surface function. And that's just what we do. We get our effluent ammonia and we assign it to the coordinates that correspond to where we are in our coordinate matrices in our results matrix. And then we'll just keep doing that for every possible combination of wastage rate and volume. So that's what our create surface function is doing, and it will be done for each of our possible scenarios. So it will create an entry in the scenario results dictionary for that specific scenario that holds our results matrix. Once we have all our results matrix, we then call our create plots function, which is another function we've defined. And we feed it the scenario list and our two coordinate matrices and our results dictionary. So let's take a look at what that's doing. We go to our create plots function. The very first thing we do is create a figure using the matplotlib library. Then we go through each of our scenarios and we create a subplot in that figure where we're going to plot a surface plot where it has our two coordinate matrices as x and y, and then our specific scenario results for a given scenario. So we're going to have 3 total subplots, one for each of our scenarios. And on our x-axis, we're going to have the volume of the aeration tank. On the y-axis, we'll have the wastage flow rate, and then on the z-axis, we'll have our ammonia. So I'm not actually going to run this simulation just because it's very time-consuming because we are running a lot of simulation. But I did run it in advance, and I have an image of what the output will look like that we can take a look at to see what this script will do. So if I pull up the figure, you'll see that we have 3 surface plots. One that corresponds to our low flow scenario, one for our mid flow scenario, and one for our high flow. And let's say, for example, we're designing a plant and our target effluent ammonia is this blue area that's present on all the plots. We want to have that concentration leaving our plant. Let's say we aren't sure what flow rate we can expect coming to the plant. We think it's going to be one of these, but we aren't sure which. But we need to meet that at all possibilities. So we can look at our plots and see our aeration flow here, our aeration volume and our wastage flow, and the effect it has on ammonia. And if we look at all the plots, most of the time it's meeting it in the low flow scenario, most in the mid. But if we look in our high flow, we can see that we need about an aeration volume of 600 meters cubed per day, or 600 meters cubed, and that can handle any of our wastage rates to meet our target effluent ammonia. Okay, so let's go back to our slides now. Just have to close the Python now. In our slides, so the next thing that we want to take a look at is we're going to look at how we can connect to an external source or an external software in GPSX like PHREEQ, for example. So if we go just take a look at what is PHREEQ? Well, PHREEQ is a program designed for simulating reactions and processes in water. And its name comes from what it's actually doing and what the equations it's applying are, where it's based on pH, redox, and equilibrium chemistry. And one of the one very good selling point and one thing of interest about PHREEQ is that it comes with a very extensive chemical database that's very easy to work with, so users can add their own chemicals to that database for use in PHREEQ. And then conversely, we can use that in GPSX. So just for reference, it's a free software and it was created by the United States Geological Survey. So if we go to our next slide, how are we going to interface GPSX with PHREEQ? Well, we're going to use Python for this. And this is going to be done using a PHREEQ Python library, which is a Python library that is an object-oriented wraparound BI PHREEQ, which is just a portion of the PHREEQ software. And what this is saying is we're just creating an object in Python that simulates PHREEQ. Now, just for reference, this library was created by the drinking water company Videns. And what are the takeaways from this example? Well, the first thing we want to take away from this is how are we going to connect to an external software package? And for this example, we're going to focus on connecting PHREEQ to GPSX. And for this example, we need to have the PHREEQ Python library, version 1.2 is what we're using, and we need to have SciPy installed, where we're using version 1.7.3, but this isn't going to be imported. Rather, it's a dependency for PHREEQ Python, but it's not installed by pip. So you'll need to make sure that you install it if you want to use this library. So if we go to our example, we're once again looking at a water treatment plant, where this time we're treating river water using a two-stage, two-phase RO treatment facility. Now, what we're going to be focusing on in this example is we're going to focus on particularly this RO unit, and we're going to focus on this brine stream specifically. So if we go into our Python script, once again, we'll go to our Python script manager and we'll select edit to open in Notepad++. You'll see all we're doing in this example is using the default GPSX template function definitions and our function call. And what are we doing? So in our start function, like we saw in our previous example, we're going to set the value of the influent flow type to be 2 so that we introduce dynamics by having a sinusoidal influent. Then we just print out a header for an ongoing reporting that we're going to do at every interval in our simulation. So if we move on to our synth function, this is where we're doing the actual work with Freq. So the first thing we do is we call the Freq Python library to create a Freq object in GPSX. And we're just going to use the default Freq database, but if you want to use a different database, you can specify using this database argument. Next, we specify the components. So first we specify what our units are, and we select parts per million because that's equivalent to milligrams per liter, which is what is used in GPSX. And then we just specify all of the compounds that are in our brine stream that are also in Freq. So for example, we're going to specify our magnesium, potassium, sodium, chloride, and a few other components that are in that brine stream. And we use GPSX get value to get what the value is in the brine stream to have it in this dictionary. Once our dictionary is complete, we pass that to the Freq add solution function, which takes our dictionary and actually executes Freq. So when we put it in here, Freq will run under externally to get a solution from those components. And what we did is then we collect we're focusing on magnesium carbonate. So we take that solution and use the total function to get the total amount of magnesium carbonate in the solution. And we convert it to units of milligrams just to be consistent with the units in GPSX. When we have that, we assign it to this variable in GPSX using the GPSX set value function, magnesium carbonate, where this is just a specific user-defined function we made in the GPSX layout, specifically for this example, that will correspond to magnesium carbonate. And then we just do a bunch of printing to report what our concentration is at every time interval. And we aren't going to do anything in our EOR function, and then we just start our simulation as usual. So let's go back to GPSX quickly and run this. So this will run, and you'll notice that you don't actually see any of the Freq simulation happening, but GPSX will simulate Freq and get its output and apply it to this to our variable that we defined, where it's plotted on this graph, and we print out the value of the magnesium carbonate in our solution at each time interval. Okay, let's go back to our slides one more time, where we'll focus on our last topic for today, which is advanced use cases. So as you saw, there's a lot of functionality that you can achieve with Python, but we just have a couple of examples that we've done some work with and we've seen for ways that Python can complement GPSX in advanced ways. So first, optimization. You can optimize a plant or use it for calibration. Python's great for that. It's excellent for external connections, as we just saw. We can connect to things like Freq or OPC, spreadsheets, or databases. You can interface with other languages. As I mentioned earlier, we have the ability to use jar files in this in GPSX, and there is an example tutorial of that. Python is fantastic for machine learning and artificial intelligence applications. Python has a bunch of statistical analysis libraries, so if you want to do any sorts of advanced statistical analysis, you can do that in Python. As we saw in our sensitivity analysis, Python is great for automating repetitive tasks. And Python also offers a way to facilitate online functionality in a simulation. So you can have real-time simulations where you're getting data from an external source and simulating that in GPSX in real time. Lastly, we're just going to focus on a couple of libraries that complement GPSX functionality that we think are particularly useful for GPSX applications. So as we saw, NumPy and Pandas are great for arrays and matrices. Matplotlib is a fantastic plotting library that allows you to have very fine, detailed control over the plots you create and the types of plots that you want. MySQL Connector Python is a way to connect to MySQL We just highlighted this one because it's the one that we most commonly use, but Python has libraries for most flavors of both SQL and no SQL, depending on what you like to use. Scikit-learn is a terrific library for machine learning applications. PHREEQC, as we saw, is a way that you can interface directly with Phreek. OPC-UA is a way to communicate with OPC to get live data. And there's many, many, many more libraries available to you that you can explore depending on what you would like to do with Python. And just as a note, if you go to this URL, this is the Python library repository, and this is where pip gets its libraries from. So if you go here, you can see all of the libraries that are available in GPSX, or pardon me, to Python.